Okay, so we are back and we'll continue from here. So we have obtained the first claim. Now let us move ahead. Since R is a simple root, of fx equal to 0 and f prime is continuous, f prime is continuous, so we can always find a delta naught, right? We can find a delta naught greater than 0 such that f dash xi is not equal to 0 for all xi in r minus delta naught, comma r plus delta naught. So the required delta lies between 0 to delta naught, which we need to choose. So it needs to be chosen yet. So for this purpose, let us introduce the following notations involving delta. Following notations using involving delta. So for example, you choose m to be the minimum of just a minute, r minus delta. You choose minimum over this of f dash xi, and it has to be strictly positive, right? And capital M to be why the minimum is strictly greater than 0, because so the minimum will be attained in this compact set r minus delta to r plus delta, and we know in r minus delta naught comma r plus delta naught f prime xi is never 0. Okay, so if this small m is 0, it means f prime xi is 0 for some xi between r minus delta comma r plus delta, which will be a contradiction. And the same logic works for the maximum. This will also be strictly greater than 0. Now let us start choosing our required delta. let us choose our required delta such that whenever x0 and x1 they are in r minus delta comma r plus delta, with x0 not equal to x1, with x0 not equal to x1 not equal to r, we have epsilon to be maximum of m, capital M by 2 small m, times x0 minus r, comma m, capital M again, and by small 2m, max upon 2 times minimum. Yeah. And so this epsilon we choose, and this is strictly less than 1 obviously. Why it is strictly less than 1? You see, because see x0 minus r is less than delta, so you can choose delta small enough such that this epsilon turns out to be less than 1. So then using 1, with n equal to 1, we can see that actually modulus of x2 minus r is less than equal to m by 2m times x0 minus r times x1 minus r, which is less than epsilon delta less than delta. So therefore we can say that x2 belongs to r minus delta comma r plus delta, and further, since mod x2 minus r is less than equal to mod x1 minus r, we can use, let us write here, we can use induction technique to conclude that xn indeed belongs to r minus delta to r plus delta for all n equal to 2 comma 3 and so on and so forth. Just a minute. Yeah. Since f prime does not vanish in the interval, r minus delta to r plus delta, the way we have chosen our delta. So we see that f is a strictly monotone function in this interval. Why? Because you see, if you have a function like this, you know, f is a continuous function, and let's say this is your r minus delta and this is your r plus delta. If it is not monotone, then it has to take a turn, right? Something, and the point where it takes turn, it will be the point where f dash xi is 0, right? So it will be a contradiction. So hence it is a monotone function in this interval. So this shows that it is 1 1, right? A monotone function, strictly monotone function is 1 1. Yeah, I should write strictly, yes, it is strictly. So this shows that f is 1 1. What does it mean? That f of xn cannot be equal to f of xn plus 1, because xn's are not equal to xn plus 1. So for any n in the natural set, hence this xn is well defined. So hence, so first point was xn's are well defined. So this was the first assumption, this was the first conclusion, that this sequence xn is well defined. You see, so we have proved this. This is a long proof. Yeah. Also, you see, you note that this entity is smaller than, as we know, we have discussed it above. So mod x2 minus r is smaller than m by 2m times mod x1 minus r times mod x0 minus r, and the way we have chosen epsilon, it is nothing but epsilon square, strictly less than or equal to epsilon square, because our epsilon was this. Okay. Yeah. Now again you go and now you do the same computation with x3 minus r, and you see it is smaller than m by 2m times mod, you just see that. So it will be smaller than x2 minus r times mod x1 minus r. Okay. But x2 minus m by 2, you know, this quantity, is again smaller than, by above, m by 2m square, or directly, now directly you conclude. So this is less than, just a minute. Yeah. I'm just thinking. Oh, we forgot one m by 2. Yes. Here we forgot one m by 2. Yeah. So now this quantity is smaller than epsilon square and this is smaller than epsilon, so it is epsilon cube. Okay, and if you keep on doing this, you will get m by 2m xn plus 1 r minus r is less than equal to, oh now the screen stopped. Yeah, so this is m by 2m times mod xn minus r times m by 2m again times mod xn minus 1 minus r. So you keep on doing this and you will get some epsilon and some power of epsilon. Okay, where this qn is obtained like this. So it is a Fibonacci sequence with q naught is same as q1 is 1. Yeah. Yeah. So now see, as n goes to infinity, this Fibonacci sequence qn, this goes to infinity, right? And as qn goes to infinity, this implies epsilon qn plus 1 goes to 0, right? Because see, epsilon is strictly less than 1. So hence this shows that xn plus 1, or let's say xn converges to r as n goes to infinity, because this side goes to 0, so this side will also go to 0. Comparison test. Okay, so from where does it follow? It follows from comparison test. So this was actually, if you note, this was the second statement that we needed to prove in the, yeah. So we have proved that there is a sequence xn in the interval r minus delta to r plus delta. Also, we have also proved third point, that is xn converges to r. So it only remains to show that this limit is the fourth point precisely. Yeah. So all it remains is to obtain the order of convergence. So which means we need to find a constant c greater than 0 just a minute. Such that, constant c greater than 0 and a real number, we need to find two things. Let's say alpha greater than 0. Alpha will be the order of convergence precisely, such that xn plus 1 minus r is less than equal to c times mod xn minus r times alpha for sufficiently large n. So in particular, or other way it can be stated as, in particular, if you are able to find c and alpha, such that limit n goes to infinity xn plus 1 minus r by xn minus r. So this limit is c. So we need to find such alpha and c. So again we shall see, we again use 1. So using 1, we obtain that xn plus 1 minus r by xn minus 1 minus r times xn minus r to be same as f dash zeta n by f dash zeta n, 2 by xi n, and this we can rewrite as, so this can be written as xn plus 1 minus r times xn minus r by mod alpha you just divide by so it is same as f prime zeta n by 2 times f dash xi n, its modulus, times xn minus 1 r times xn minus r 1 minus alpha. Okay. So where alpha is an appropriate number to be found later. So again we do some manipulations, and to find alpha we further rewrite the above equation as so what we do, So left hand side is as it is, and then xn minus r by xn minus 1 minus r times alpha whole power beta. So beta is actually 1 minus alpha, where beta satisfies the equation beta equal to 1 minus alpha and alpha beta is minus 1. So if you solve it, so we solve this for alpha. So how should we proceed to solve this for alpha? You see, 1 minus alpha is beta and beta is actually minus 1 upon alpha. So this implies alpha minus alpha square is minus 1, and hence alpha square minus alpha minus 1 is 0. So if you solve it, alpha is actually 1 plus you use the quadratic formula b square minus 4ac, b square minus 4ac, yeah, by 2. So therefore alpha has to be 1 plus root 5 by 2. We choose the positive square root, and this is precisely what we need to prove. I mean, this is precisely the candidate for the order of convergence. So in this way we get this. Now so by the sandwich theorem, we see that since zeta n converges to R and xi n converges to R, and therefore we have limit of this quantity to be equal to f dash r. Why? Because see, f is a C2 function. Again and again we are using the continuous twice differentiability of f. So combining all this, we get that limit n goes to infinity xn plus 1 minus r by xn minus r alpha, it is same as f double prime r by 2 f dash r limit n goes to infinity xn minus r times xn, just a minute, yeah, xn minus 1 minus r mod alpha times this. So you just put everything, okay. You see, we have this limit and if you put it here we'll get the required thing. Okay, yeah. So finally so alpha we have been able to find out. Now we seek the finally we seek C such that C is C minus 1 by alpha. Okay, and clearly because the property of alpha, this solution is C equal to this. One by alpha, and this fortunately completes the proof. So this was the longest proof in this discussion session that we have done. This completes the proof. So so now we have this convergence theorem, yeah, for the secant method. And yeah, so see, the point is this convergence theorem assumes a certain things. For example, the function that you're working with, it should be C2, that is continuously twice differentiable function, and R should not have, F should not have any other root. Like no, what I want to say is that any root of R is a simple root. If there is such function, then we can apply this secant method and it will ensure the convergence around R. Okay, but again the hypothesis, see, even in the conclusion you should note that you have to choose your initial values to be sufficiently close to the simple root small r. Okay, so yeah, so we have completed the proof. So maybe I will discuss the next method briefly. And that method is called the Newton-Raphson method. I will maybe continue this in the next lecture also, but let's see how far I can go with this. A quick introduction is always possible. Yes. So it is again a root finding algorithm, as we have seen in the secant method. This method is a root finding algorithm which gives successively better approximations to the roots of a real valued function. So again, this method, the aim of this method is nothing different than what we have already done and studied for the secant method. So the so the idea is to start with an initial guess. Okay, I'll just give the geometric interpretation, then we'll continue this in the next lecture. The idea is to start with an initial guess. Then to approximate the function by its tangent line. We'll see what do we mean by it. And finally, to compute the x-intercept of this line. What is the x-intercept? The point where the line intersects the x-axis. The x-intercept of this tangent line this x-intercept will be a better approximation to the root and the next iteration in the Newton-Raphson method. Better approximation to the original function's root than the first guess. And you can continue this method for iteration to obtain the iterative sequence. The method gives a sequence of iterations. So geometrically, see what is happening. You have xy axis here, and let's say your graph is this. Okay. So first what do? You choose your initial guess. Let's say here, this is your x naught. Yeah. So this is your x naught. Oh, sorry. Then you draw a tangent at this point. What will be the tangent? Yeah. Just a minute. No. I want to draw a tangent. So tangent will be something like this at this point. So the point where it intersects the x-axis precisely will be a second iteration. The first iteration. So see, instead of working with 2 points, we are working with only 1 point, which is contrary to the secant method. But yeah, we will see, we need actually sufficiently smooth function for the Newton-Raphson method. Now again you repeat this process. Okay. So now you draw the tangent again. Yeah, so your tangent will be like this. And where does it intersect? It intersects at x2, let's say. So you see, this is the root r, and you are moving in this direction, and eventually you will go to the original root r. And that is precisely the idea of the Newton-Raphson method. We'll see some derivation of it in the next class, but let us see what we have done today before finishing. Okay. So in the last class we have discussed the bisection method. So in the beginning of this session today, we started with the secant method, which is a root. So see, throughout the discussion from past few classes, the aim has to be how to find the root of a given function. And that function need not be linear. Now it can be any function, for example, sin x plus x square or something of this sort. So f can be any function. At any given point, the methods that we have been implementing, we need at least continuity of the function. So secant method is one of those methods which gives us concrete algorithm to find the approximations of a root of a given function, such that with every successive approximation it gets closer to the root. At least the idea should be like this. Okay. So what are the secant method works with the existence of two initial guesses. We have to guess two initial values x0 and x1 such that f of x0 is not equal to f of x1. Now geometrically we have already seen what do we mean, how do we do the method. You join the line passing through the points f of x0 comma f of x0 comma f of x0 and x1 comma f of x1, and you continue this line to intersect at the x-axis, and that will be a unique point, and that unique point we are taking to be our second approximation. Now you do the same thing for x1 and x2, you will get x3, and you keep on doing this. So we formally derive the equation of this method. We saw some drawbacks, and the drawback is that if initial values are not close enough to the root, then there is no guarantee that the secant method converges. We saw one example, sin x plus x square minus 1. How does it work? Like just the implementation of the formulas. Now the big shot of today's discussion is when we discuss the convergence of the secant method. So the hypothesis for this theorem is that we need a C2 function, and how to find a sequence via secant method which converges to a simple root of f. Okay, f need not be having a simple root at all, but we are adding this in the hypothesis. So for this particular class of function, we have a very good convergence in the secant method, and it is approximately equal to 1.62, which is more than 1 and less than 2. So the secant method is not quadratic. Order of convergence of secant method is not quadratic. Then we saw the proof. It was very long, but in the proof one thing was very, very clear. You have to have an explicit you have to make explicit use of Rolle's theorem and mean value theorem again and again up until the first derivative, and that is why we have taken f to be a C2 function. Then in the last I tried to discuss this Newton-Raphson method, but due to shortage of time I think it will be a better idea to discuss this in the next session. So unlike secant method, Newton-Raphson method just need one approximation to start with. Later on we'll see that whereas in secant method you don't require, in the formula you don't require f dash, that is f prime, but for Newton-Raphson method we'll assume that f is at least differentiable, once differentiable. If a function is once differentiable, then you can apply Newton-Raphson method rather than the secant method. So you just need one initial guess, and Newton-Raphson method under certain hypothesis will ensure that the method converges. It gives you a sequence of approximations which converges to the root of the function. Okay, so yeah, just a minute, the screen just stopped. Yeah. Yeah. So in the next session, what we'll do, we'll discuss Newton-Raphson method. We'll be discussing Newton-Raphson method. Its geometric motivation we have already discussed, but with the help of this geometric motivation, we will be deriving the formula for the Newton-Raphson method as we did for the secant method. Once again, it is not that difficult. You just compute the tangent line equation, and your next iterant will be solving the tangent line where it intersects x-axis. So then we'll see some example, then the convergence for Newton-Raphson method. Yeah, so maybe we will move into that direction. Then after that we'll see interpolation problems. Yes. So yeah. So all these methods that we'll study are highly useful in the numerical computations, because most of the time the problem is you don't know the root. And it is not always possible to explicitly find a root. But given a certain error bound, you can always approximate this root via these methods, secant methods and Newton-Raphson method. And there is another method called regular-Falsy method, which is a pre-generalization of secant method, or of which secant method is a generalization. But all these three methods give more or less a good approximation to the root. One over another might be better, but that is up to the usage of the function. So you have to be very careful which method to use, because when you will be submitting these method to the computer, and it is always better to save time. Less computations means less propagation of error, as you've studied in the beginning of this numerical analysis course. If there is an error at some stage, say 1 or 2, and if any computation involves that particular value, so the error will be propagated. So we don't want that. Okay, so always the less computations are better. So you have to choose a method. For example, for a given function, you can always apply secant method or Newton method, let's say, for a given function. Then you have to choose which method to apply, which method will be better. Okay, even if both the method converges to the same root, it might so happen that one is converging to the root, given a certain error bound. Secant method is giving that value, let's say, after 10 iteration, and Newton method is giving let's say at 15 approximation, or the other way. So you have to choose which method. Obviously the method which gives better approximation at less iteration is always better. Okay, So with this we finish.